Let's discuss problem 6. It is asked that find RAB. From looking from these two terminals, you have to find the resistance. I have given a hint that you have to do series parallel reduction, and you have to find the resistance, the equivalent resistance seen from these two terminals, which is usually shown like this, that you are standing here and looking inside. And what is RAB? To solve this kind of problem, you can it's more easier to identify nodes and then proceeding further. I would like to do few comments here, that some student they think that current is coming here and it is flowing in, it is dividing into two parts, so they make 6K parallel with 5K. But this is wrong. You can, it doesn't matter that you are starting from the right hand side. Usually it's that if you want to find the resistance from these two terminals, equivalent resistance, you start to wrap from the other side. But you can always do something in between if you want. For example, if I want to reduce 3K and this 3K, I can do it right here. It doesn't matter I must start from here, but some in between, if you see something and you want to simplify that, it would not matter. But you cannot reduce these two resistors because the current is being divided. The other condition is still there, that it should be between the same two nodes, because as I have discussed here, in a node pair voltage is same. If it is V, all of them would have V volts, and we have found that already here. But if this is some other, is this node and this node, the problem is like this. In these two nodes, between A and B, we have, for example, this A and B, we have 5 volts. But this 5K is not between A and B. It is between some other, there's a third node involved there. So you cannot reduce that just by seeing that if the current is being divided. So that is a typical mistake. But if you want to reduce 3K and 3K, you can do it here because they both are in same node pair, and the reduction would be between the same two nodes. The idea is that if you want to reduce a parallel combination, you will reduce a loop. A loop will the loop would be gone. And if you want to reduce like this one, this 3K and this 3K is between two same node pairs, so you can reduce them and this loop would be gone. Similarly, this 3K can be reduced with this 4K if you want to start from here. They are in parallel and between same node pair, and current is being divided, so you can reduce that. So whenever you reduce a parallel combination, you reduce one loop. And when you reduce a series circuit, you reduce one node. For example, this, if I start from this node here, you have to start from nodes all the time. If you start from this node here, there is no current, is not being divided here, so current is same in 4K and 8K, so you can say, and it is between the same node pair, so 4K is in series with 8K. So that's why I have written 4 plus 8 is 12. So this is I have reduced this node here. So still the resistor is between this node and this node. You can see already here, this 6K is here, this 5K is here, 3K over here, this 3K. Okay, this is further reduced here. 8 plus 4 is 12, and 12 is in parallel with 4. So this is this 3K, it's in the straight one, and this is done in one step. 8K plus 4K is 12K, and 12K, which is reduced, is between the same node pair, and 4K is also, so you can directly write 4K parallel with 12K. And this is easier, that the parallel combination can always be found by their product. Means if I want to find the parallel combination, it would always end up into their product divided by their sum. 12 plus 4 is 16K. So 1K is cancelled. So 4 3s are 12, 4 is cancelled, 4. This is 3K, which is shown here. So this one is actually 3K reduced between these two nodes here. So we have replaced this circuit by a 3K resistor, and this is 3K is in parallel with 3K because this is same node pair. When you reduce between the same node pair, you can reduce this loop here. So 3K parallel with 3K is actually half of that, because the product divided by sum. Okay, this is in fact like this 3K, so this node and this lower node is here, upper node is 3K. I'll just write this one 3K, this 3K over here, and the reduced of this one, which is this one, this 3K here. So these three resistors are in same node pair, which the same idea which was here. In the same node pair you always have the same voltage. So if they have the same voltage and current is being divided node, and so you can see that node current is coming here, also here and here, the source is on the left hand side, then they are in parallel. So you can this can be in 3. If you want to reduce 3K and 3K, I always know that this is half of that. So 3K multiplied by 3K divided by 3 in their sum, which is 6K. It is 9 by 6K, which will be actually 1.5. 3 3s are 9, 3 2s are 6, and this is 1.5K. And if you reduce further 1.5K with 3K, so their product divided by their sum, this is 15 3s are 1.5 is 4.5 divided by 4.5, this is 1K. So it is shown here, and the formula was different. 3K was the LCM, and 3K into 3K, that was by using the other method. So but I think this is fine. You can just pair two resistor and find this, use same formula, and then pair the reduced one with the other one, and like this one, and find the equivalent resistance, which is shown here. It's 1K. Now you can see that the current which is flowing from this node is not being divided, and they are same current is flowing through these two resistors. So within these two nodes you will have a new resistor, which is the sum of these two. 5 plus 1 is 6K. So you can say 5 plus 1, reduce any one of them, and then write here 6K between these same two nodes. This is 6K. In this node pair you can see this is a node, upper node and lower node, same idea here, and you can reduce these two into, so whenever two resistors are in parallel, they would have same node, they would be in same node pair, and current would be divided, and same resistor in parallel have always the half of the resistance, so which is 3K. So the resistance seen from here is actually AB terminal is 3K.